Hey, afternoon, everybody. Thanks for coming today again for now day 3 of our webinar. Just, to make sure that everybody is able to hear me, just because I don't think my camera is working. It just looks like a spinning wheel to me. Just let me hear. Thank you, Emily, for confirming that you can hear me. Yeah, we'll have to see whether if my camera works here or not. Otherwise, because I'm coming to you live from ASCPT in National Harbor, Maryland. And as I, here, VJ led you through, the concepts of kind of population PK modeling and, being able to describe a lot of the terms that are going to pop up again today as we get into a little bit of a practical side now and working through kind of a full modeling example. And today we'll run you through a base model fitting for a very well-known, warfarin, model, where we'll start off. Really, again, I want to make sure that you understand, even if you don't understand the code, you don't need to come in here having known anything, about pharmacometrics, but understanding that workflow, understanding the information that's needed so that, when you read this code yourself, you're starting to understand and you're able to kind of make a gross interpretation of what this chunk of code is meant to do. Because having that is going to be your first step, when you go into tutorials and start expanding things into kind of more complicated setups. It's the journey of 1,000 miles starts with a first step. And as I also understand, a lot of the examples from yesterday, talked about this, one compartment, IV bolus model. So I'll try to relate that and we'll build on that because, of course, warfarin is primarily, we're considering it's an orally administered drug. So there is a little bit of a difference just in terms of what we will eventually have for our differential equations and the setup of our model. But before, I get into that, I just want to kind of give you a brief overview and, kind of thought for the workflow in terms of a population PK model fitting. And, similar to the NCA workflow, it's actually going to be very similar in terms of the thoughts. And then, remembering that in terms of our helper functions. So the first thing that we would have is, we need to be able to read in some data and, generate our data set. For the purposes of today, and just because I want to make sure that we get through the model block and actually, the fitting, more of a population PK fitting, we have, files under the population PK folder, kind of 1, 2, and 3. We'll probably be glossed over today. And if we have time, we'll jump back, and I'll try to highlight, maybe some of the key items just where I see, maybe where people are starting out with Julia, just some things to be able to keep in mind. But, this is a kind of curated, very well-known, sort of data set. So there isn't a lot of data wrangling and, modification that has to go on through here. And again, on part of the last day, we're going to point you towards some of the, other areas for further training in Pumas and the Julia language. So, and that has some great examples in relation with data wrangling and the database setup and, initial plotting. And I will fully admit, data plotting, using the algebra graphics, if you're used to things like ggplot in the R platform, it's a little bit of a different sort of mapping, but it's very, it's relatively easy and intuitive to catch up on. And the example in, file number 2, it really does give a step-by-step process. So please let us know, when you go through and try your first visualization using, this data set, if you run into problems, leave us a note on the Discord channel, ping us, originally, and we'll help you out to get you on the right track. So after you have your data, we need to be able to define the population that we're going to analyze. So in the NCA, we had used read NCA. Well, similarly, for the PK population, we now have a helper function called read Pumas. And we'll define, and match our variables and our columns from our data set that are going to be essential then for defining within our model and, for our estimations. Of course, along with that, and the added item, of course, this is a PK or potentially PD or PKPD. We need to actually develop the model that we're going to have. So that's a little bit of an added extra step, and we'll walk through the development of that model block. And for those, the handful of you, some of you have, non-mem experience, you're going to notice, some of these things are easily translatable and very similar, and that's a little bit by design. And then once we get into our read Pumas, we defined our population, we have our developed model. Technically step 4 is more similar to step 3 with the NCA process, and we actually want to perform the analysis. And that analysis for NCA was in run NCA. Well, we don't necessarily want to, perform an analysis. The point and, the terminology that we're using for population PK models is we are performing a fit. And so that is where we use the fit function. And then once we have those fits, there are, several different, statistical diagnostics and visualizations that you'll want to run on your model. But, the 4 kind of key aspects to be able to get to an initial result, something that for you to be able to kind of look at, understand, do the parameter estimates, do these population estimates make sense, falls into kind of 4, again, that 4-step type of category of data set, read into population, define our model, and then actually perform the fitting. So let me jump and share my screen at this point. All right. So at this point, everybody should be able to see the same, VS code space area that we've grown to know and love over the past 2 days. And again, today we are going to be working in this population PK folder. And for the purposes to kind of piggyback off of what you started to learn with VJ, I'm going to actually jump and, kind of go into our model definition first. And, for this, again, we're using this warfarin-based, PK model. And before, we read and kind of digest the model that's down here, I really want to just first give you a background on, what is it that we need to, and, if we're developing kind of a model from scratch. And the most important thing to kind of, understand, from this in terms of the Julia language, we use macros as a way of inserting code into a program. And we see that, through the use of the @ symbol. And so, in this idea of we're using this Pumas model item is being defined through an @ model, or, the model macro that you may, hear me kind of, describe there. And kind of with all of our blocks, as we, kind of see, and, you can infer a little bit from our, example already here, there has to be a beginning and an end. So just to be able to even start building your model, we'll just give it a name, and, I'll just put MDL model. I will, again, push you towards good labeling habits. Don't just label all your models as model, whether, it's model 1, model 2, something a little bit more descript, something like for your final model, it's the final warfarin, PK model. This will help if you ever have to start and, build an actual reference to be able to show, what it is that you did and what you evaluated over time. You just have all your individual models numbered. And so you can show, and in your own mind and your own files, kind of show a clear series of events. But just to generate a model, all you need here is at model, begin and end. So right now that creates an empty model. So components, and we're going to start throwing around a lot of words that VJ was talking about yesterday. And I'm going to throw in here most of our kind of individual blocks that we can consider. So there's a lot. We won't necessarily use all of these on a regular basis, and I'll try to point out to you which ones are are most commonly used items here. But let me walk you through, just in a very quick context, what each of these areas is going to cover. And this will make more sense when we actually start going through and building a model ourselves. So the first one here is the @param block, which kind of makes a little bit of sense. It's your parameter block. It is defined and used for specifying your fixed effects. Similarly, underneath, we know that there is going to be some level of random variability, and we define those random effects in our @random block. Covariates we can pipe in under @covariates. And for the purposes of kind of our base model, we won't necessarily be focusing on a stepwise covariate model or anything like that. We do have in this particular model, just because it is a developed model, there is a covariate for those of you who I am sure are reading ahead, because I know I was one of those. These are actually allometrically scaled, whether for clearance or volume components, that they just loop in already using the weight-based dosing. I will show you when we get to that part, because usually we're going to want to also potentially estimate those exponents for allometric scaling. And I'll show you just, kind of how we modify the code, from this, just to be able to allow that. But otherwise, this is where you put in your covariates, things like body weight. What's something that, like for an antibody based, drug, albumin tends to be, heavily studied, just because, other protein-protein interactions are going to cause, potential effects on the disposition for PK. If there are going to be, things for PD modeling and things for, potentially, liver function tests. So your AST, ALT, ALK phos, diabetic patients, you throw in your glucose levels, all of those get defined just under covariates as a list that you can then eventually pipe in to your actual model. The pre-block, initially, I didn't understand was, well, what does pre mean? And really, this is pre-processing of the variables needed for your dynamics section, which if you kind of jump ahead, the dynamics section is the actual dynamics of the model, which I know can be a 4-letter word for some people, because that's where our differential equations are going to start to come into play. And, that can get really dirty really fast, depending on how complex your model is. And again, I'm always a fan of have tablet and paper, draw it out, draw your circles, draw your lines, very similar, what VJ was showing you yesterday. And that way you make sure that you check off all your kind of components and everything is flowing as you are visualizing it in your mind. Dose control. So these are going to be various dose control parameters that are going to be present in your model. For those of you with, again, non-MEM experience, this is where a lot of your F block sort of items are going to be. But this is primarily where we'll look at and have things for bioavailability, lag components, or, when we get into more kind of advanced absorption models, things like the rate and duration used in 0-order kinetics versus, 1st-order absorption kinetics. At vars, it's more like variables. It's an area used for shorthand notation that is able to go in there, and that may or may not be used. It just kind of depends on your coding style, and it can help you just so you're not having to fill up. Commonly, if you think about like a typical Emacs style model, like if you have a nonlinear elimination, you can define something so you can provide a shorthand notation for that nonlinear effect. So you're not, having to put in 4 different, making sure you have all your parentheses in the right spot at each time, which I got to admit, it can get, quite daunting at times. Is the screen being shared? Can't see anything. Sorry, guys. It should be. Is everyone else able to see the VS Code space? Oh, it's being shared now. Okay. Sorry. Again, I'm working remotely here, so I'm only operating with 2 screens right now. I miss my 4-screen setup, from my home setup. Again, you can tell the level of nerdiness of your pharmacometrics by the number of screens that you get used to having to use. To kind of round out the last of our individual, blocks that we may have, we also have the @init block. Again, this is something that isn't going to be commonly used, but is really important because you can define the initial conditions for your dynamic system. So I've most commonly had to use this in considerations for pharmacodynamic modeling. There are instances for PK where, this is going to be, important. And, this is where, if you don't want to assume something as being at 0, or if there is going to be a certain set type of baseline, you're able to augment kind of what is the initial starting point for your dynamic system using this @init block. But that's, it's a little bit more of a niche kind of need and use, in your kind of starting out population PK model development. You probably won't use this block quite as much. We already mentioned, dynamics is, our differential equations. And that dynamics block then leads really into our derived block, which is actually where the statistical modeling of the dependent variables is ultimately stored. And a final block, again, that's used really for kind of purposes is the @observe block. And this is where you're actually able to use model information to be able to store and use it for particular solutions. So what we or a example that I commonly will use this for is, we can run a PK model and we can actually run the NCA analysis as part of it. So, as part of the output of the model, we can have it pipe in or figure out a AUC, 0 to 24 hours of the AUC tau. And potentially then for combined, more advanced models where you have PKPD, you could pipe that exposure back into then, say, the pharmacodynamic, say a theoretical, indirect, response model. So again, it's something that you can get into. You can have it output, even something as simple as just being able to provide you, the half-life. But it's allowing you to be able to kind of make some initial information, but feed it back into the model system itself. So with that kind of in mind and knowing then where you kind of started, with VJ, I want to, start you and kind of work you through how I would go through and develop a modeling block. Because it is not necessarily going to be in this direct order. Sometimes once you get, used to it enough, yes, you will be able to kind of copy paste a bunch of your, initial reference code and just to be able to change things up. However, for the new initiates, of us, we can try to help it so that it's a stepwise process to make sure that when you complete one block, it feeds into the other to make sure that you're capturing all the data and all the variables that need to be defined. So with that, usually I like to start with the @dynamics block. And so that's where we actually will define our, if I could spell, begin. So again, each of our individual blocks will need a beginning and an end, and we need to define our differential equations. And, admittedly, I am not one of the cool kids. I don't have the Mac, and I can't do the whole pen reading. So I'm going to do this old school and just, PowerPoint this up. So, in the example that you had yesterday, you were doing an IV bolus model. So, we are assuming this central kind of compartment. So we are treating the body is one uniform giant blob, of volume of a certain size. Coming out then of that, you would have your clearance and, the elimination of the drug, from the system. And so we'll call that, CL. It is going to be important when you are naming things to be case specific. When you are going and it's looking for things in between each of these blocks, the difference between CL, CL, and CL are all different variables. So when you are using certain things, and some of these, I'll show you also some quick shortcuts that Pumas has built in. So you don't necessarily have to type out all of your differential equations for some of the more commonly used types of models. You want to make sure that you're using the correct notation moving forward. The other component here is we also kind of know we need to know about volume, and so we'll have our VC kind of this artificial it's almost like a scaling component really that we're going to be using. And so how would we derive, what is our differential equation? And so let me pull up my list here and let me random number generator go Jacob. I'm going to get to pick on Jacob today. Are you there, Jacob? Sorry. Have you ever had any experience in writing a differential equation before? Oh, Jacob might not be there. Let's try somebody who has talked. Oh, you're there. Okay. So have you ever written a differential equation before? Nope, don't think so. Okay. So this is, it may sound daunting, but it's really not that bad, because really what is, and I'll throw this out as a generalized kind of question of, in general, what are we kind of considering for a differential equation? What is it intended to do? Well, for the sake of time, I'll kind of move us along here, but what we are wanting to really make sure to define with our differential equations is to discuss the movement of the amount. When we are talking about these differential equations and defining things within our models, we're dealing with a amount of your drug, and part of that there's really a transformation that's occurring. So it's a transformation being applied into a particular compartment. You can think of it as that way. And that is, how we're going to write our, individual equations. So if we think of what is that transformation, It's a little bit, more simplified in this initial one compartment model, because really the only thing that's occurring here is that we have drug leaving from our central system. Because the initial, bolus application of our drug is considered to be immediately and fully contained within that central compartment in the example of the IV bolus, example. So then how would we define that rate of elimination coming out of the central? Well, we know, sorry if you give me a second here, that it's going to have to be some level of negative value, because it's going to be an elimination from that central compartment. And let me just kind of give you, again, we're doing this as transformation times part is our generalized kind of what we are hoping to move from here. And so in this example, just to be able to get things out of the way, the compartment that we're dealing with is the central compartment, as we're just calling this central. It could be called plasma if you're going to be more descriptive, if that's where it's coming from. If you have other compartments here, peripheral compartments that are meant to be maybe tumor specific drug levels, if you're doing certain oncology models, it could be called that, and this all gets added on. But ultimately, what is it that our transformation is occurring? The change that's occurring here is an elimination of the drug based off of this clearance. And because of, with concentrations, as, we're going to be inputting our data, because our, dependent variables, and I fully agree with, I was around when Vijay talked about how DV has just been terrible, for everybody to be able to have that just named that way. But, the data that we are inputting here is usually a concentration. It is a nanogram per ml. It is not just dealing with nanograms. So our clearance is, a kind of volume per time, and our volume is occurring. So what is our transformation coming out of here? It's clearance by volume, and removing that from the central compartment. So in terms of actually setting this up, central prime, that's our differential equation. So not as difficult as you might think, right, Jacob? And this is where, when I'm talking about, having a pen and paper, draw it out. Draw out each of the arrows where things are going, because this is where you're going to make sure that you're capturing all your different variables and all your different compartments. So let's take this one step further and make this applicable. Are you sharing some slides that we can only see the VS? Oh, is it not showing my screen? Hold on here. It might be, that's what I was doing. It was only doing that. Apologies, everyone. So now everybody should, you can see this PowerPoint slide. Yes. Okay. Apologies. So this is, again, to, as the refresher, we have the central block, this volume that is kind of representing kind of this, artificial volume. It's, more of like a scaling factor, for this individual blob that is representing the human body. And then we have an elimination pathway, essentially, it's going out to nowhere because it's being eliminated, defined as our clearance. So again, this is our transformation sort of component, a negative times central. So this is actually good. And so thank you for pointing that out before we moved into, complicating this further. So now let's, make this a little bit more applicable towards the warfarin, model. So now this is an oral drug. We are not injecting the drug, IV bolus directly into the central compartment. But now, it's having to travel through the gut before it reaches that kind of theoretical central, plasma compartment, starts circulating through the body. So typically what we end up calling that is a depot compartment. And if you, again, just forgive my quickly trying to type this out. So it is that, and you can think of this as kind of almost like the GI tract for those if it helps you visualize it a little bit better. How is that drug? Is it going to go directly GI into the central? Is it going to work both ways? What should the directionality of the drug out of this new depot compartment be in relation to the central compartment? No takers? So think about it, if when you pop a pill into your mouth, it's going into your GI tract, and it's going to then, go through, and while this is a gross simplification, to be able to get into the plasma, it's, unidirectional. But that is going to be defined by its own absorption rate, and Ka is usually, what we're terming, you'll see most commonly used as our absorption rate constant. So I'm sure, Ka is something, that has popped up. Ka times depot, exactly. So good. So that is going to be, what is, part of our differential equation. Now, since, Emily, you put it up, how would you define the differential equation then for your depot compartment? Oops. Good. So it's minus because it's leaving the depot. So that is going to be minus, and you don't necessarily have to have the parentheses in there. I'm just putting it in there just so we're keeping this as a that is your transformation and from the depot. Good. So then how do we also need to modify the differential equation for our central compartment then? Because we already have this component. What else needs to kind of get changed? I know typing this out, we'll take a little bit of a second here. Good, exactly. So if you think about that, this is what's being eliminated. So that is representing this arrow. We also need to take now into account the drug that's actually coming in. So really that is, the easiest way is to think about it is you can take what you had as your negative, you have to have it as an input somewhere else. So exactly as you had it, I just have it, tagged at the end. So our Ka times depot, we now have a positive amount of drug coming into our central, and it's also then being defined by an elimination based off of our clearance. Good. Excellent. So if we define that in dynamics, there are a couple ways that we can actually perform this. So we could write that out ourselves, and you actually saw kind of the notation that I was using. So if we use this, we can define the name of our individual compartment, and it's important. So, whoops. Sometimes it likes to autofill things if you don't add an extra space at the end. So just watch out for that. So it's important, that when you're naming your compartments, they're going to be the same thing. It is going to be looking for that. As well as then whatever you define your parameters here are going to have to match whatever is in your model block above, later on. And then we can go down and we can write in our central compartment. So we'll do this, I like to think of it as, addition and then subtraction. So your Ka, or sorry, and this actually, it's a negative. We want Ka times depot. And then we will subtract out our clearance and volume times central. Super. So our 1 and 2 compartment models are probably some of the most common, models that are going to be used. And for those of you who want to be able to shorthand this and use fairly common nomenclature, there's another way around this. So for those of you who don't like to have to write out your own differential equations blocks, we do have some shortcuts. And that is through, the use of shorthand of depots and central and peripheral. So for that 1 compartment IV model where we only have a central compartment, we can just write this in as dynamics central 1. And if we actually look at the help screen, so again, if you hit shift, question mark, central 1, just to see what it is that it's defining, right at the bottom, it's showing that this is, what that analytical model. And so it's exactly what we had just written out kind of in that PowerPoint diagram. So all this is going to make sure is you want to make sure that you're using big C, big L for clearance, big V, little c, and terming, central is going to be your primary block. And if we wanted to add this, in for the oral, depot 1, central 1 is also, another one that we have off on there. And if we, quickly just take a peek, you can see that just using that, it's the exact same differential equation set that we just threw out. So you wouldn't even need to define that. You can even just simplify it down to here. So when you get into, indirect responses and, more advanced, sorts of models with 3 compartments or more, depending on the branches, these types of shortcuts are not going to be as efficient, but, you can use this and then also peripheral 1 as an example of, a base, 2 compartment model type. For the purposes of kind of keep this as similar-ish to our Warford model as possible, I'll use this and use our shorthand of, 1 depot compartment and 1 central compartment. But knowing, just remembering, so CL, VC, KA, depot are really what we're going to want to define. So we have our differential equation. Cool. So what is the next kind of area that we may want to, start working on and filling in next? Well, we just finished the dynamics block. And, well, in the name and the kind of the description of what we discussed for the that's pre-processing for the dynamics block. So we'll next usually fill in our pre-block. And so this is where probably the more typical kind of, equations and, where we start to define our individual estimates and our application, kind of where random effects are going to occur, are defined. So, for the purposes of, whether this it's, one compartment IV or this, also oral model, what are, some of the parameters of interest that we're most interested in having to define likely for our model? And admittedly, you're going to be able to cheat a little bit just because you're going to be able to actually see, some of these already pre-written into our Warfarin model. But, what is it that we are, most commonly estimating? And remember, we took it out of the dynamics block, so that should also give you, the idea of what we need to feed in. Exactly. So, we need to define our clearance. We need to define VC. and we need to define Ka. Because this is kind of feeding in and looking at, again, pre-process into the dynamics block. So we need to be able to see what it is and how it's handling each of these estimates. So when we are building this in, and this is where I'll try to show you and infer a little bit when you get into covariate style of modeling. Ultimately, when you build out this necessary set, you can specify all the necessary variables and the inter-subject variability. The inter-subject variability can be handled whether separately or as a matrix, and that won't make necessarily a little bit of sense to you until we get up into the parameter block. But I'm going to show you an example for each of those. And when we're looking to define each of these, what is our total when we're dealing with clearance and all of the various effects that could be occurring, what is and let me put this out to everybody and see what we get. So when we're defining clearance, what are kind of the sum effects that are occurring that will define clearance? And the word effects is actually, I probably should have used something different. That's a little bit of a hint. So that's part of it. Good. So, you're thinking about it, you already got it. So you're kind of starting to think about, residuals that are going there. So what exists too that isn't necessarily the random effects? And again, this is where I kind of walked you through our total blocks first, because ultimately, each of these individual blocks is going to define some of the effects that we need to account for in the model. So your random effects are defined in your random block. Does anybody remember what the param block is for? Covariate's true. So covariate effects will be another thing. And what's the last? Starts with an F. So our fixed effects. So typically when we're going to want to write out our pre-processing, you can think of it as your fixed effects times how are you going to define your random effects and potentially covariate. If I could spell for worth it, I'm just going to put a code. So since we're dealing with a base model, we're not going to be dealing with covariate effects implicitly saying, again, using the example of like for monoclonal antibody therapeutics, those with lower serum albumin levels have different dispositions in the clearance of the antibody compared to those with normal or high levels. Do take into thought that there are more structural components. And so typically you do see a lot of allometric scaling occurring, and this warfarin model does perform that. So that's kind of outside the typical kind of covariate model, and some of that is applied implicitly, just from what we know, within kind of just within our field. But let's start filling these in, a little bit, at a time, and we'll start with clearance. So for our fixed effect, we can call this whatever we like. You will hear this referred to, and it's a theta parameter, so it could be theta clearance. You can also see it with the annotation of it's the true value or TV clearance. Personally, I'm more this way of TV, and this is an estimate. It's not true value. It's the estimate of the true value. Always remember these are estimations. And just so you know, you can use the actual notation if you wanted to apply, the actual theta. If you use, backslash and start typing in, what you want for theta. So you have, and I cannot remember the appropriate name. It's not ASCII code, but you can apply, things and show it as theta CL, etas, omega, all of that through backslash and start typing out whatever that Greek letter is. And so if you use big O, M, omega, that's going to give you uppercase omega. But if you use lowercase omega, it gives you the lowercase version as well, just to be able to have that option, again, for whatever you choose and whatever, fits your fancy. The important thing will just be that this nomenclature has to be able to match eventually what's up in your param and random blocks. Whereas, the definition of this pre-processing is what has to be able to show in dynamics. So we defined our fixed effects. When we define our random effects, typically, this is going to fall within an exponential, and, in the most common cases, we'll have this. And, this is where, what we typically term, and somebody correct me if, VJ Dan mentioned this, but, this is typically where, we have our eta variables occurring. So we can type out, eta. And this is where I was talking about it can be individually coded eventually or as actually a matrix. So if we are looking at a matrix where eventually we'll have, random effects, say, on clearance and volume of the central compartment, we can have that matrix and pull, the estimate from the matrix in the first position within clearance and second for VC. Alternatively, if you want to individually code this, you could just call it, A to CL as well. And just knowing then you aren't going to make a single line, which is going to reflect a matrix, but you would have in your random block individual eta translations. For the start and for kind of ease and realistically, actually, the more complicated models, I personally like having the individual blocks, but I will fully admit that within Pumas, I will eventually end up, using matrix annotation overhead. Just making sure with the outputs you'll see, it's going to talk about eta 1 and eta 2, and you just have to remember and which it is or which variable it is going to be assigned to. And while we're not going to have a particular covariate effect, let's apply a allometric scaling kind of component onto this. So if we had our baseline body weight, we'll normalize this to a 70 kilogram person, again, assuming that baseline body weight is going to be based in kilograms. And if you already know what that allometric exponent is, for clearance, a very common, estimate is going to be starting at 0.75 for clearance and 1 for volume. So if we want to, just use a fixed parameter initially, because we don't have a lot of data potentially, especially, in the world of, your first in human studies, SAD, MAD, you're not going to have a lot of data necessarily to accurately estimate this, but realize, eventually you can also estimate this exponent as well. And one way you kind of end up shorthanding this is, we can define another parameter here, the allometric scale on clearance. And just include this up there. So it makes it look a little bit neater in terms of shorthand. And I think this helps, especially for larger models. It helps with the computation time a little bit, if I remember, correctly. We can define that allometric exponent and essentially just pipe it in to the next, line below. So there we have it. This is, our initial build then for clearance. And, for a similar effect then, Somebody, let's pick on Emily's been doing a lot here. How about Robert? So Robert, what would our fill-in for VC be? So you can start it out as, what should our fixed effects be? Followed by a random effect. And then I'll tell you that we'll typically also have an allometric scaling exponent to this, right? So type it out for me. Good. So, right. So we'll do, say, TVVC. For our random, we'll just be able to call this, and just because I don't want to have to retype it, I'm just going to copy paste. We want to make sure that it's a separate. So in this matrix notation, if they're both 1, it's going to estimate and assume that the random variability for clearance and volume are the same, which doesn't make a lot of sense in our case. And then we'll define something called like allometric scale volume central. And again, if you just excuse me copy and pasting just for brevity. And you don't necessarily, since this is raised to the 1, you don't need it, but I'm putting it in there just so you're able to see that. This defines our block. Great. And then similarly, just for completeness, we will do KA. So you can see when you're copy and pasting, when you're starting to build this, certain things just start coming together. And it just ends up making, kind of sense and, feeds in. But again, what we defined in the dynamics now is kind of put into place in the pre-processing block. So now we need to make sure to define like, okay, so where are we defining weight BL, TVCL, and these, random effects, sort of notations. And that's the 3 blocks up ahead. So for ease and brevity, I'm just going to start, covariates. We need to make sure we pipe in weight baseline, of course, because we call that in. If you have something like an albumin level, you can type in albumin. And when you're making a list in this sort of fashion, you do not need the colon notation that would denote, individual column headers. There is, the version kind of down here within the block, or it is the same way here. I'm thinking of DeepPumas, sorry. I'm jumping ahead into different things. But when you have multiple items, coming out here, you do not need that column. You don't need a comma. It's just separated by a space or multiple spaces. It's forgiving. Whether you have that and that, it still recognizes that it's not adding on, extra spaces into your file. Unlike, in things like non-mem, where you have to be very cautious about the number of spaces that you have and where they are, because those will actually mean very different things. For param, I like to do param before the random, but I will just add in our blocks as we begin. So again, our parameter block is intended as our fixed effects model or fixed effects estimates. So what is that, as defined within our pre-block? Well, that's going to be our TVCL, our TVVC, and TVKA. So I'll just make sure, we'll start out. We'll need to define what each of these things is, TVVC and TVKA. Now, this is not going to be a equals type situation. And just to be able to show this too, typically what we will have is and I can never remember, it stands for in. Essentially our true value is within a real domain, and we have a bunch of different, separate keyword arguments that we can use. What this is kind of implying, and maybe let me, step back here. So again, the param block is meant to indicate really just the simple PK related fixed effects that occur in, these key parameters that we are attempting to specify. You have an individual one per each line. You're not going to have commas or, anything to kind of muddle this up. So it helps you, self-organize going in, with the ecosystem. And we just need to define these different domains. In most cases within the param block, you are going to use real domain. And, there are several different types that you can use. And, the kind of simplified version to think about for the real domain is that it's going to be scalar parameters. There is a option for vector domains, and that's of course the use of vectors. I will be frank, I have never used that or seen an example actually where vector domain has had to be applied in the past 4 years. So focus param block and real domain. The other two domains, the pdiag domain and PSD domain, which you'll be able to see examples of down in our true warfarin block, are really something that we're going to consider for our at random block. And so I'm going to hold those discussion for those two off until we hit the at random block. And really the only difference between those two is really, are we going to evaluate just the diagonal effects versus the full matrix of effects? But again, we'll touch into this, going forward. Typically then for the real domain, the most common keyword arguments that we're going to want to define is potentially, a lower and upper bound, for the actual estimate. And you can define, if you wish, the initial estimate here. So instead of defining, a name tuple, vector later on, you can actually, provide the initial estimate within your model block, and using some of our, kind of keywords later on to be able to help you. It just simplifies, your life a little bit by having it contained within the model. It also helps that if you are then sharing your model, say example, your final model that, Emily developed a model and now Robert needs to perform some simulations. If she copies her model block over with the initial parameters from her final fitting already present, well, he has all of those final population estimates already set up and ready for his simulations, ready to go, and he can just port those directly in. He doesn't need to make sure, typographical type errors occurring, of course. So to kind of, again, finish off our, block here, typically, having set its value 0 or something, really small is going to be able, make sense. We can't have a negative clearance. At that point, then we're generating material. And of course, using, your initial estimates should come from a informed kind of perspective. Typically, you'll have an NCA analysis beforehand. And so, I'm just going to make up some values here. But, you don't want to just throw in random numbers in there just because you do run the risk of, are you going to get stuck in some sort of statistical well as it's, trying to optimize, and converge in these kind of log likelihood ratios and the best fits. So you don't want to just, start off with every model and just label the initial as 10. Don't do that. because you can run into trouble, especially later on down the line. So we defined our fixed parameters. So now let's deal with our random effects. So first, we're dealing with, I'll show you kind of the matrix, annotation. Or actually, sorry, let me step one step back here. Or actually, no, I'll keep going. I take that back. So what is the first thing that we're going to want to apply? And so we're going to need to define what this eta, matrix, ultimately is made up of. And you can see examples, down here in the random block. So, this is a little bit more descriptive, it's the eta for the PK variable. And that is just because I do provide you an example of a combined PKPD version under this additional materials box. So then we do have a PD eta effect as well. And in this case now, we're not going to be, piping it in, and we use this, tilde, symbol. And really that is just, the tilde notation is just going to be, used to, mark and going into our, what is our distribution going to be. And, while we can use multivariate normal, or, even define a normal distribution, and, just being careful of what you may need to have as your inputs. For each of these, we use square root of, this particular omega value. And I believe, and again, correct me if I'm incorrect, that, VJ talked the difference likely between the different types of residual and IIV versus, items. So omega versus eta values. The square root of a standard deviation is variance. And typically we are going to report our random variability with a variance. And so to make sure that we are defining, within our normal distribution, Julia likes to be able to see, its mean and standard deviation. So if we have our omega for tabs as a variance, we need to convert that into a standard deviation first. But you can just do that through simple mathematical operations. So I'm just going to copy and paste that up here. And we'll just leave this as omega since we talked about that. So this is now where you also kind of need to bounce back and forth a little bit because, okay, we have these fixed effects. We have this matrix of random effects, but we never actually now, we're defining, this omega. So, where is this coming from? And so that too is something that needs to be defined, with our parameter block. And that is where instead of real domain, we have these, and I believe, okay, we use p-diag domain, in this sort of case, or, oops. Sorry, so let me type this out, so slash, so our omega. So either it's p-diag domain or PSD domain. And again, the difference, looking at this is just whether it's going to look at just the diagonal, remembering that, as a matrix, this is going to be where we have 0.9 and then 0.0, 0.0. And if you give me 1 second here, this is not, the most elegant way of demonstrating this, but apologies, to do this with time. This is probably the best way for me to be able to show it. So the p-diag domain is going to focus solely on this cross diagonal. So, we're looking and we defined the random variability for clearance as the first item, VC is the second, and KA for the third. it is not dealing with the interrelation or what we term as the covariance among these individual variables. So this can be problematic, especially as you start getting into covariant models or true kind of covariant models, because volume of the central compartment can be related to a whole bunch of different things other than just clearance or Ka. And if we need to account for that to reduce the variability and as it may explain interpolation variability, we actually want that model to estimate these off diagonal components, and that's where then you will switch into a PSD domain. But what you will end up having to initially set that is defining an initial estimate, or initial estimate, and defining that then matrix of our initial estimates. And this one, you can, if you know something about the data, you can put it there. But in this case, it's a little bit safer to be able to start at a kind of arbitrary relative kind of number. So using 0.05 or 0.09 as the variance there as a starting point is usually pretty safe. So now we have our omega, our fixed effects defined. We have those omega parameters fed into our random block, which defined as our eta parameters. We have a set of covariates that are going to be piped in because they need to be used within our model. We can pre-process those into our variables of interest that are used within our dynamics block. The final thing that we'll need really before you can then wrap this up and actually be able to run an actual model then is to finally the derived block. So we need to focus on and actually figure out and state what those assumed distribution of these observed variables are being derived from all these blocks that we just typed out above. So in the case of PK, this is where we're going to have kind of a initial I like to call it CP. It's the concentration in plasma, and then dV. Just because again, this is what this second one should actually equal the name of the column that you're going to be actually pulling your data from. So if this is dV plasma, if it is called umbopolonium 01, fine. Just make sure that it matches, because that is what it is ultimately trying to specify where it's pulling from, what is the name that we're trying to attach it to. And so while the concentration, again, our dynamics blocks deal with the movement of amounts, we need to convert this into volumes. Our basic kind of block for central is just being able to convert that at any point in our dynamics. What is the concentration going to be? It is going to be the amount in central divided by VC. I mean, it's an amount over this volume. So that gives us, concentration. So what is the difference then of what we need to consider for the dependent variable and kind of in our real world example? And so that's where we need to take into account, we already have random variability kind of take into account, in our pre-block, and that's fed into the dynamic. So what's the other type of variability that VJ talked about yesterday? So we kind of already dealt with IIV through our random effects. We have fixed effects. What is the final type of variability? Does anybody remember? So that's one spot of where it could occur. And there's a term kind of for this. It's, it's variability that we're not really going to be able to fully explain. Starts with an R. Or also, correct me, did VJ talk about residual variability? RUV, potentially? I thought I remember him talking about that. But, when we define this, this is going to be, whether it's just added variability that we are unable to be able to account for and kind of explain, within our models that can't be explained through the randomness on clearance or volume essential. And that variability can take many different forms. It could be additive, where it is kind of a flat rate going across, regardless of, concentration. It could be proportional. So, we're going to have, a shift and change over time, or, the more complex sort of operators are, can be a combination of both. And ultimately, what we're going to want to do is, that is going to then assume some form of distribution. So we're going to want to use our tilde, and we can define then whatever distribution we want, whether it's log normal, you can just have regular normal, distribution. Realize, one of the benefits of Pumas and with the non-mem world is everything is assumed to fall within a normal distribution. And we know that just is not the real world case. So one of the benefits of this is we can actually define what types of distributions we want to use. So we can use gamma and beta distributions for things like bioavailability. We know that, especially for bioavailability should be between, 0 and 1, 0 to 100%. You cannot have a negative bioavailability. And, for some of these things, within a normal distribution, it's going to be captured, incorrectly. And so that's where things like beta and gamma distributions are, particularly helpful, in things like bioavailability. Or if you find out, like for your random effects are not normally distributed. They may be skewed towards one side or the other. And so you do have that option of, you do not have to assume and use a normal or multivariate normal operation. You can use beta and gamma distributions there, or even more complex, statistical coding there. Again, for your purposes in starting, let's just use a normal distribution. And ultimately, what you're going to want to, for a normal distribution, what are we going to want to, define? We want, what does that mean? Kind of central tendency. Well, we define that above. It's CP, so our concentration P. And so that's going to usually be whatever we define up there. And then the second half is going to be kind of the effect of that residual variability. And so whether that's additive, we are going to actually have to define something here. So probably what he may have, or what VJ may have mentioned, sigma values, similar. And, this will use a similar, it's based off of as a scalar. And so let's just, if you pardon me again, trying to quick, we'll do an additive and a proportional sort of item. And we'll set the initial as, say 2.5 nanograms per ml as a flat kind of additive effect for the initial estimate, and 10% for our proportional. If we were to define the additive rate, it would just be the additive rate that has to get added in. So it would just be additive. If we are having a proportional, we need to know what that proportional rate is based off of it. Since it is a proportion of something, it needs to be based off of that concentration. So our residual variability, whether it's additive, proportional, individually, or if you start smack everything together, oops, you end up with something like this. When you are building your models, other than individual structure types, so, whether it's a 1, 2, 3 compartment model type, you will test, where and how many, different, eta values, and, where does this random variability exist with and without, allometric scaling exponents. Is it an additive, proportional, or, is combination, or potentially even an exponential, where then you can just do whatever, it's kind of an exp of a sigma, whatever you want to call this, or, sigma value. And that's, adding in and, trying to describe then that unexplained error, that residual error, that RUV that is, occurring, found within your observations. So in terms of being able to build out your initial model, that is the key. These are, that is the base, the minimum that you're going to need to apply to be able to get your model, to actually build and run. So let me try, walk you then through the model definition for our PK model now that we've been through all of this. And I know that was a lot. So please, I'm trying to watch the chat box here. If something else, keeps coming up, stop me as we're going through this. So take a quick sip of water. Again, I would start out here in our dynamics block. Based off of what we know from the literature, this is well described as a 1 compartment model, and it's an oral drug. So this is kind of the long form version of being able to, we wrote out the differential equations with depot compartment and a central compartment. So when you are setting up also too in your data sets, when we're talking about like compartment 1 or compartment 2, this is what's going to define that. First line, compartment 1. Second line, compartment 2. Realize, again, another benefit of Pumas, you are not stuck to having to use numbers. You can define the compartment as depot or central, plasma, tumor, whatever have you. It does not need to be numerical because then especially as you start changing things up in terms of structures, it just causes, fewer instances where you actually have to change your data set. Because now, let's say if we do a second compartment or you are testing, immediate and sustained release types of formulations. So then you actually have 2 different depot compartments. Well, now your dose isn't going into compartment 1. It's actually going into, 1A, which will be your, say your immediate release. And so you have to make sure that you modify your data set so that it's reading in the dose lines correctly. Well, that's a pain. Again, planning and thinking ahead is going to save you a lot of time, in the future. Going up to our pre-processing, we have our theta values, so our fixed effects models being defined. This kind of predetermined allometric scaling exponent based off of body weight, which is already kind of just included within the individual data sets. And then that random variability. And again, it's defined just as the PK eta, just because there is another version down here to be able to show you, kind of a combined PKPD version. And also, if you want a little bit, I included this, model block 5B. It's a little bit more of a guided walkthrough of kind of what we just did as well, just explaining what's in each of the blocks. And, has a couple links to some other of our tutorial sites, just so you have that as you're trying to, potentially self-learn later on down the line. Kind of interesting, just as, a oddity in the way that some people may report some of their, data. They give the absorbance half-life So they don't give you the actual Ka value. But of course, the smart, clinical pharmacologists that we all are, and, PharmD, sort of training that we have, we can convert that half-life into a rate constant. And so that's what we actually do here. So now we have, this Ka, Cl, and Vc that are defined in dynamics. And we define all those up here in the parameter block. Again, get in the habit of, notating and adding notes for, what it is that you're trying to set up, and, as reminders to yourself and others. One thing I will, point out is if you add these kind of headers in, these are metadata, so that when it is estimating, theta clearance, it is going to associate and add a tag for this longhand on it, which, in some of our other COF tables, when we do data summaries, you're not just going to spit out theta CL. It'll use the actual label, metadata label that you provide. So again, it's just another little extra shorthand, as well as providing, some added information for, Robert made, a model, and now Emily has to be able to translate it, but Emily doesn't know what the heck Robert has been working on. And so, we're able to define, it's like, well, what the heck is theta tabs? Why don't I have a Ka? Okay, well, there's absorption half-life is what theta tabs is equal to. If we go down to pre-process, it's a half-life, and we're converting and we're deriving the Ka within the model. So again, adding notes, adding things, not just for yourself, but whoever may use it later on, is you just being kind of a friendly scientist to, the next person down the line. We also do include a lag component, which I'll touch on. I'll show you, a version of that within our dose control block. We define that random variability, so those IIV, so our omega for the PKs. In this case, we're basing it off of a diagonal. We're not looking at those covariances that are occurring. In this case, we're only applying this onto CL and VC, so there are only two. And so there are only two in our initial predictions or initial, setup. And we have an individual omega setup for that IIV on the absorption half-life. And then we define both the proportional and additive error, residual random unexplained variability. And just to be able to show you an example kind of within dose control, adding a lag component. So, for an oral, drug, it may not initially show up, within the plasma, where you're being measuring, immediately, or, as quickly as you may expect. And so we can add in this additional lag component. Essentially, you are defining that there is a certain lag of time before any amount of that drug will leave the depot compartment to get into, this case, the central compartment where you're measuring things. Again, our typical plasma compartment. And so that's one thing. And, we could add in here, a bioavailability component if you had sufficient data to be able to know or know already what that bioavailability is. And just to, show you an example with the VARs, while we defined CP down in the derived block, we threw it up here just to be able to kind of show you the example of, what is that concentration in the central compartment. And then ultimately, the conc, concentration column header is what is found within our data set. And it is based off of a normal distribution based around a mean of that CP. And this is a little bit more of a longhand version, but a way to be able to show, both a proportional effect and an additive effect combination residual error model. So that is our kind of PK model block. And I know that is quite a lot to go through. But when you are reading non-mem or publications, having an understanding of what the individual nomenclature, so that idea around fixed, random, and residual variability is really important, so that okay, I read this statement, I know which block that it's going to have to end up going into to be able to translate this, or to be able to take a non-mem file that maybe somebody developed a base model of something back 10 years ago. And now you're translating it into Pumas for further work because they created a backup compound or the next third generation of something. So let me stop here and are there any questions or clarifications that I can provide you just talking about this kind of model block? Okay, I'm not seeing any inactive typing. So let me jump kind of into the next part of our fitting. So again, to just keep beating it kind of into your brain, we in theory have a data set already set up and kind of data wrangled. And at the end of this number 3 file, we now developed our PK model, in model number 5, and admittedly I have to delete all this just because I pipe it in so it won't mess up. So then what is the last thing we need to do before fitting? We need to define the population. And so that is where we will use read Pumas. And what we're going to need to do then with this is, similar to read NCA, we just need to be able to define, several of the keyword arguments, and, just be able to define what is it that we need, or what is the equivalent that is being piped in from our observations. And so if we look at the documentation too, we have quite a bit. So if you forget, kind of what some of these arguments are and what they should be, we provide you a little bit of, guidance here of, what the options are. But there are going to be, sort of a set number of critical, and mandatory sort of items. So the first thing is, let's, give it a name. And so, pop underscore PK, nice and easy. Make sure it's descriptive enough, potentially. Just if you know that you're going to run into multiple populations or you're dealing with multiple different, for example, whether you're dealing with different patient types or subsets of data, just to make sure you're not everybody. Again, not everybody is pop. The first thing that we're going to read into that population to define what is that data set. And so DF wide is ultimately, so it's a wide form version of our data set that we actually, it's the end product of number 3 or file number 3. And you can actually run that if you want already. If you just run all this, it's actually quite a little thing, and I will use this. So when info is popping out, it's the one benefit of having these info in my day-to-day life. I do not use these at infos quite as much, just because it is only going to show up as a line within your REPL. When you're running things, individually or within a singular file, you don't necessarily gain any benefits coming out of it. I will say that that is not necessarily going to be the case, and it's good to have that to be able to segment what is occurring where if you end up going onto the actual Julia Hub platform versus running locally, because if you distribute your job, so you're not using a local system, but you're actually kind of sending it off into a virtual machine to run in the background where you can then pull the analysis afterwards, and something errors, it'll let you know how far along in the process it ended up getting before airing out. When you look at the error code, you're going to be able to see the individual at info lines, and then an error pops out. It's like, okay, well, at least it got to this point, so like our error had to have occurred from here on. So we're importing our data frame. we will need to specify the subject identification. So in the case for our ID, I'll just, try to pull up here on the bottom. So DF wide. We have 32 subjects, and ID is our ID, and we specify the column header by using a colon, ahead of it. We will need to provide the time information. So in this case, we just call it time. And again, with CDIS standards, you'll see NFRLT, AFRLT, and PRLT. As probably more common sort of items later on, within your industry and, clinical lives. But for the purposes of this, they made time is time. You're going to need to provide the actual dosing information. So we need to provide the amount of drug that is being dosed, into what compartment. And so this is where, we still use, in this case, 1, 2 things. In this case, 1 is the depot compartment that we know based off of the PK model that we just, had developed, and the event ID. So it's important to know that for amount and compartment, that typically you are going to have, amount will just be only on dosing rows. Typically for compartment, at minimum, it needs to be available for dosing rows, because you need to know where you're applying the dose. It is also good practice to have a compartment for your observations. So the non-dosing rows, just to be able to know, like, okay, this is a concentration within compartment 2, which is our plasma compartment. So not as difficult in this example, because we only have one central compartment and one area where we could actually feasibly collect concentrations. But once you start collecting and you'll have 8 different pharmacodynamic markers, you have 2 different PK sites, you don't want to mess those up. So again, you having that description, just know that that is available to you as you're developing these things. And then similarly for event ID, there should be something in every single row. And for those of you who have never had to deal with this in the past, an event ID of 0 is equivalent to an observation. And typically an event ID of 1 designates a dosing row. That gets a little bit different in terms of if you are dosing a placebo. So where you actually have a dosing event, but you're not actually applying any new drug, you'll use an event ID of 2. There are certain instances where, there are event IDs of 3 and 4. I am not going to go into those for you, because that is just going to blow your mind. And the uses of those are very specific. So if you don't need, I have had to use that once in the past 10 years. So it's not super common. So again, most common example. We will also pipe in which covariates we need to work with. It is important to know, compared to the @covariates block that we use within the model, it is typically what I like to do is actually define, within the PK model, go down, copy, that line, whatever you use for, covariates, and then make it essentially, you need to add in the colon to be able to denote the column head and commas between each of them. So again, this is set up more because of, our program and, these quote unquote kind of standards and how you should lay out code. It does help out in terms of adding comments. So I will, add and say that, there is some benefit of doing this, especially, where sex is not necessarily always labeled as M or F or male, female. But, the old style of 0 and 1 to keep it, numerical. Just realize you do not need to, again, for all these things, you do not need to have everything just as a numerical value for your covariates. We can handle male, female, or MF. It doesn't need to be a 0, 1, 2, 3, 4, sort of setup. And then finally, and just realize you may not have any covariates to pipe in, especially like very early on base model development. So this is, fully optional of whether you actually need it. But if it's in your PK model, it needs to be within your population, because otherwise it's not going to know to be able to apply that and carry it over, within your population and into your fitting. And then finally, your observations. So this is, where is your actual drug concentration? So in this case, we have a column called conc. And so this should match your final line in your derived block. So ultimately, that is just really taking your data frame and just you're speccing it out. You're matching it up so that Pumas is able to understand, what is the data and where it's coming from. So also too, if we run that, it gives you a spot check and a little bit of, a data summary. So in this case, it's 31, subjects we defined with sex, or these, 4 covariates are being piped in, and the observation name is under conc. You can actually look at this, examine the actual, object just to make sure. It's like, well, we have 32 labels. Like, is there one, like, what is the actual length of it, confirming, whether it's 31. You can actually look at a data frame from the actual population itself. And again, so it's going to look very similar to your data set, but now it is, added items that, based off of read Pumas and knowing kind of what you're piping in, it has things set up and changed, added rates, duration, II items, and, roots, things that, will be considered for when we actually move into the fitting. We can look at individual data if we really wanted to. So looking at like that first subject or the first item within that population. So this first subject 1, it has 1 event with 7 individual observations and, covariates. And you can ultimately, examine each of those too, if you needed to, similarly, just to save ourselves, some typing, we'll just call subject is equal to that first item within our population. And we can look at, and actually, I did forget to kind of mention this. If you don't know what options are available in terms of, sometimes with keyword arguments. So if we write out subject dot, and then I hit tab twice, it gives you a listing of what's available as a possible option afterwards. And it gives you there. So we can type in, okay, that's an option. So let's look at the events. So for that first subject, it gives me the dosing events lines. So for this, single kind of dose study, it's not overly complicated. When we get into multiple dose studies or, more long-term phase 2 efficacy studies, it is nice to be able to spot check yourself to make sure that when you import your population, that somebody has the dosing occurring when you expect it to be occurring. Alternatively, because in the real world, people are terrible and don't take their medicine. If you know that there are certain subjects where they didn't take their med and, they actually had a deviation or, they had a known stopgap because of an adverse effect that occurred, you can spot check that person to make sure that your model, before you go into a fitting and you're fitting something incorrectly, are their dosing events correct? So, being able to look at their events, observations, and, individual covariates just on a individual level, but after defining your population is a nice little spot check, sort of situation for you to be able to kind of go through before you spend the time. I think the worst model that I've ever had to run took 8 hours to run once. You don't want to mess up. You kind of, just 8 hours of your life to realize, oh man, like I should have done a 0 versus a 1 in my data set in Wrangling. Like, now you got to go back. You just wasted a day. And, you know, depends on who your boss is at that point, whether they're going to get grumpy with you or not. And, you know, similarly, this is just, you know, more of a spot check of being able to show that the length, you know, based off the unique IDs of our data set matches the length of the subjects, you know, defined within the population. So it's, you know, 31 and 31. And so they purposefully skip a number to kind of throw you off a little bit. So super. You know, I know that is a bunch of information, but like what we just covered in the past, you know, about an hour and a half, this is probably the most foundational and 2 parts to really drive home to be able to get your fitting set up, and what you will change as you are exploring and developing your population PK models. Because ultimately you're going to have tens and worst case, you know, maybe hundreds of different models developed, you know, for an individual drug, where you're going to have to test individual compartments, covariate effects, types of residual variability, random variability, you know, the interaction between certain covariates or certain covariates on certain parameters. Each time you have to set one of those up, you know, you're going to have to create a different model block. And that is where I will recommend having and actually setting up your models as individual files that you will then pipe in, because otherwise you can imagine individual files with a whole bunch of models. You know, it gets hard to navigate those sort of files. And, you know, ultimately you kind of end up using one file as your dashboard, kind of for, you know, being able to run your fit and then perform diagnostics. So again, just to kind of beat the system into there, we have a data set, 1. 2, define the population. 3, define the actual PK model. So now 4, we're finally ready to perform a fit. And so I'm just going to run each of these models or items again. Again, this is just an easy way. It's reading in the Pumas data, so the population gives us our read, you know, pop PK object. We're reading in the PK model, so it reads in our PK model. Execute our handful of, you know, packages and libraries. And so I mentioned this a little bit earlier. So this is where the init within our model block, and you are a little bit of a helper. So instead of having to type out your own kind of name tuple and making sure, okay, well, did I include all the right names? Did I include everything that's already within my model block? You can actually just call that information already, just using init params and then the name of your model. So you can see that if we actually pipe each of these in, it gives us the same exact output, regardless of whichever method, you know, that you end up using. The benefit of using something like init params and ultimately this style of notation is, you know, as you are doing stepwise sort of model building, you know, we will test the structure type 1, 2, 3 compartments first, and we'll take the initial effects there. We can then pipe in the coefficient estimates from that particular model directly into our next iteration. We don't need to have to manually type out the numbers each and every time. Again, typographical errors and, you know, human beings are, we're flawed. You know, we're going to make mistakes. We're not going to make 100% or shoot, you know, 100% of the time. So, you know, getting around this, and we'll show you some examples too within the fits, just where you can kind of pipe that in to help optimize some of your workflows so that your models flow into each other seamlessly. And you're not just spending time, well, copying down numbers. At that point, you know, it's almost like you're just creating your own Excel file, and nobody wants to deal with that in their life anymore. So when we want to perform our fit, we call a function called fit. It kind of makes sense, right? And within that fit, you can imagine that all these individual steps carry some sort of weight. So what's one of the first things that we need to define? We need to define the actual model. So that warfarin PK model from file number 5 is first implemented. We have to define the population. So the output from what we ultimately did in file number 4 is provided there. So pop PK. We need to define what the initial estimates are. So whether you wrote out your own vector of initial estimates or you use the init params, you actually don't even need to call init params there. You can actually just have it set up where it's here, and that's a nice easy because this is the model. We're pulling the starting values from the initial parameters of model. So that's just one way you can kind of scapegoat yourself. And then finally, we need to provide the estimation method. Now, FOCE is what we're going to provide you, initially here. Probably the most commonly used item for pop PK, analysis. Just know there are several different types of fitting estimations. Things like naive pooled, Laplace, Poisson, evaluations. Each of these carries their own specific uses and needs. You need to make sure you understand why you're using it versus, a more kind of universal kind of estimator that, this FOCE kind of ends up working with. So when we run this, again, based off of your individual machine, since this is a local sort of run, will vary in the typical speed. The first time you use a function, sometimes it requires a little bit of an extra thought process just to be able to get things running. But you could see that what it was doing, if I kind of interrupt and go up here, it's checking the initial parameter values. And so it's making sure that, those initial estimates that you provide, these init params, don't cause like infinity errors and nonsensical sort of outcomes. If that happens, again, that's where we want to make sure that what we are putting in isn't just some rando number, because ultimately you can run into problems where your model won't fit because you just offshot, you're 1,000-fold off, the initial base. And so it's just not able to converge on any form of solution or estimation. So it's checking that first before it starts ticking through iterations. And so you can actually see what is the functional value and, the time that it's taken. And so it, performed that first evaluation 0.017 seconds. And ultimately it looks like it ran through 94 iterations of the model before it ultimately converged. It took ultimately on the computer time and only took about 3.2 seconds. So super fast. And just realize, more cores on your computer doesn't always translate to faster. The complexity of the model and how the model is coded can also lead to differences in how fast these things go. For the purposes of like our smaller style models, you really won't notice much speed differences between things like Pumas and NAMM and R. But as you get into more complicated models and where you start, combining things, PKPD models, or, where things have, direct responses and, these immunodynamic sort of models that are used in like vaccine research or, certain types of models that are also used in infectious disease for kind of the bug drug kill sort of effects. Those can take, they seem like very simple sort of models, but they end up eating a lot of computational space because you have so many different things parameterized that it's all trying to, estimate at once. I think I've had the worst model that I've ever, I shouldn't say worst, but the most parameterized model I think that I've ever run was it tried to estimate 42 individual estimates. And you can imagine like it's having to change and modify all 42 of those within each other within bounds of random variability. You can just imagine like no human would be able to handle that. It just boggles the mind. But at the outcome of that fit, we are given this little, summary. So were we able to get a successful minimization, and, a nice little kind of summary of, initially log likelihood, the number of subjects. It was optimizing. None of our parameters were fixed. Now, that is not meaning fixed effect. It is meaning that we held a parameter constant. Like we defined our clearance as 0.2 versus allowing it to actually be estimated. We allowed it to optimize 9 individual parameters, and giving you, a summary of kind of the total number of observations in each. And then we have a base summary of, the estimates that it's popping out. Always good to be able to look at these and like make sure, does this jive and does this make sense, with the information that we know about our drug. So, a 0.33 nanogram per ml concentration, that's not bad. About a 9%, proportional error, that's, not too bad here. There's quite a bit of variability on that absorption, half-life, component. When we translate these into RSE percent, which I will take pity on you, and I am not going to grill you on the standard deviation, standard error thing, because I think VJ got enough out of you guys yesterday. I felt a sigh of relief already all the way here in Maryland from that statement. And then, just our individual, fixed parameter effects that we're moving on from there. So now that we have this initial fit, we can start looking at things, whether we want to be able to check kind of convergence, check on, whether we hit, the final local minima, and go into diagnostics. And I'll try just to give you an intro to get into the diagnostics before we kind of end for today. So one of the things you may want to look at, and your PIs of interest may want to look at, is the convergence trace. And what this is going to show you is kind of a plot of really based off of the iteration of, are we achieving the lowest level of log likelihood and that gradient norm. So usually we want to be able to see not something that is squiggling all over, that we're seeing this nice kind of drop off and it's maintained essentially relatively flat, and these little bumps is where it was trying to find its final iteration, value. And ultimately, we can also look at the parameter uncertainty by looking at the inference. And, if we infer that, again, I'm not going to grill you guys on this, but this is, that same, it's a standard error that is being put there. And so when we look at this 95% confidence interval, this is based off of, this standard error estimate. This is not, something, depending on how much variability you have, it is fully possible that you could have a confidence interval which reports a negative clearance. That doesn't make sense, right? Remembering, how your estimates and what each of these outputs is actually telling you is important, just, really for the interpretation. So this will help us, these are information that we will still need for determining, RSE percent, for each of our parameter estimates, and that you'll see reported in typical parameter summary tables, that you're going to have in any sort of publication. But again, caution when talking about, the confidence intervals, associated with each of these. This is also kind of, as a summary. You can use the COEF table sort of function just as a summary of what each of those, and again, we're pulling it from this inference to be able to give us, essentially a data frame that we could eventually, perform other mathematical operations or, use summary tables, table 1, to be able to summarize, as well. What I want to point out is, whether you use or don't use the metadata, coef table versus coefficients table. And coefficients table pulls in that metadata. So when we look at it, it gives you that description. So it makes it a little bit nicer. So again, like, what is omega 1? What is that relating to? And it's so, well, it gets cut off here just in the REPL, but we know it's the IIV on clearance, whereas omega 2 is the IIV based off of the volume. Model refinement. This is the example where, okay, we ran one fit. Sometimes it's nice to be able to run, especially for your initial model, just run the prior parameter estimates from where they are, just to make sure you're not stuck in some energy well. But instead of having to type out, a new model block and to be able to take in, an entirely new, extra 30 lines of code, we can pull in the coefficients from that first model fit. Now, this is a little bit bad, so this should be like model fit, V2 or something, to be able to run a second fit, but it's going to pull the coefficients from the results of that first fit for your second fit. And otherwise, we're using the same. It's the same structure. It's the same population. It's just now that our initial estimates that we're using are the results from our first run. And ultimately, it comes out to be pretty much the same thing. So that's good. It's a nice, tech check tech sort of item. Now, if we had some extra information, or there are certain items where you want to fix a known variable. So in this case, we have a really high variability around that absorption half-life. And we know, maybe there's some other data that, the real world example is really, it's only, it's half of that, or, less than that. We can define, the initial parameter still fine, just fine, but define and, fix one of these as a constant. And then using the keyword argument constant coef just within this fit object, it knows that that omega tabs is going to be a fixed parameter. It's not going to try to estimate that anymore. So that's where, when we run our quick fitting here, again, it's checking the initial parameter estimates. Now, when we look up here, there was one fixed variable, and that is our, omega tabs. Let me stop here, because some of these will just go, and it'll be good for, well, essentially tomorrow we'll start with diagnostics and finish up, with some simulations, and kind of round out, now that we essentially at this point we have now fit a model. Now we're, performing some functions to be able to, analyze our model to see how well it is fitting. Is it appropriate? And, in a real world example, what is the next step that we would need to take in our model development? So I'll stop here. If you have to go, feel free to go. Thank you again for coming for day 3. We'll, pick up again tomorrow. I'll stay on here for, a couple more minutes if there are any questions or, clarifications that I can provide in the chat at this time.